Okay, we're back. We're continuing on with our solutions chapter. We are going to talk about heats of solution today, enthalpy or heats of solution. We've done a couple demos in class that I have not put on YouTube and probably won't, so hopefully you can recall those. This is sort of a recap of that discussion. As you recall, when I took ammonium nitrate and dissolved it in water to form ammonium ions and nitrate ions, remember AQ means essentially dissolved in water, the flask was cold to the touch, in fact quite cold to the touch. So we had decided that this was an endothermic reaction, so heat was required for this dissolving process. And in class we put the symbol for heat, delta H, on the left hand side of the equation, and we said, well, when we have an endothermic process, delta H belongs on the left hand side of the equation. Heat is required. So if you hold that flask in your hand while it's dissolving, the required heat is coming from the surroundings, and as you're holding it in your hand of course becomes part of the surroundings and heat is taken from your hand. So once again, this was an endothermic process. Now if we had a saturated solution of ammonium nitrate, we will put delta H on the proper side again. You'll see the arrows going both ways. So when it's saturated, if you recall the definition for saturated solution, we've dissolved as much as we possibly can at a given temperature. So we have some dissolving occurring at that point, but at the same rate, some solid is forming. So we have an equilibrium. So we get to think about Le Chatelier's principle again. So what would happen to this equilibrium if the solution were heated? Well, you remember in class we drew a silly picture of a fireplace, right? And, we put some wood in there and created some flames, and we had a little girl who came in from the cold. And we said, okay, if that girl is cold, in which direction is she going to go to relieve her stress? And all of us said, well, she's going to move towards the heat or towards the fireplace. Well, she might get too warm after a while, and so to relieve that stress of being too warm, which direction is she going to move? Well, when she's too warm, she's going to move away from the fireplace. Well, in our reaction here, our symbol for delta H is analogous to our fireplace. So, what would happen to this equilibrium if it were heated? So think Le Chatelier's. Well, wouldn't it shift to the right? So we wrote in our notes, it would shift right. Do you recall that? It would move away from the heat when it gets hot. It would not move towards the heat. So, would ammonium nitrate be more soluble in hot or cold water? Well, AQ means dissolved in water. We want it to move to that side. So how do we get it to move to that side? Well, we'd make the water hot. Recall, if we made it cold, then we'd shift to the left and we'd make more solid. We want it to be more soluble, so we'll shift to the right. Now this demo we did not do because sodium hydroxide is very corrosive, so we're fairly careful with that. But we said pretend that you were holding this flask in your hand and it got warm. So sodium hydroxide, as it dissolves in water to form sodium and hydroxide ions, heat is released. So that's an exothermic process. And for exothermic processes, delta H goes on the right-hand side. Okay, so we put delta H on the right-hand side because heat is a product. Heat is being released during the reaction. So delta H, our fireplace, goes on the right-hand side. Well, what would happen to this equilibrium if it were heated? Wouldn't that be the opposite of above? If this equilibrium were heated, we wouldn't move to the right and go towards the fire or towards the heat. Wouldn't we move to the left to go away from the heat? Because this time heat's on the right-hand side. So in this case, equilibrium would shift to the left. So would you suspect sodium hydroxide to be more soluble in hot or cold water? Well, if we want to shift to this side where the AQs are, dissolved in water. We want to shift to the right. We want to make it colder so it will shift towards the heat. So we circled cold in our notes. Then we sort of shifted direction and we started talking about gases and their solubility in liquids. And we said, how does an increase in temperature affect the solubility of gases? And we said, gas solubility decreases with an increase in temperature. So as the temperature of the solvent increases, the solubility of the gas will decrease. And we wrote in the bottom of our notes, we said, for this, if you remember, we drew an arrow, and we said, think about soda pop. So what does that mean? Well, if you open up a bottle of soda, you don't store it outside your refrigerator, you don't store it on the stovetop, you keep it in your refrigerator. You keep it in your refrigerator because the gas will stay dissolved better in the solvent as the temperature is colder, because as we get an increase in temperature, the solubility of that carbon dioxide in your soda pop drops and it will lose its fizz more quickly. Then we related this to fish. We talked about trout and why they're inactive fish and how they need oxygen. Oxygen, of course, is dissolved in water. So why do trout go to deeper water in the summertime? Well, because the lower temperature in the deeper water creates more O2 AQ. Recall, AQ means dissolved in water. So the lower temperature, there'll be more oxygen dissolved in the water. So they would go to deeper water where it would be cooler. We said catfish, bass, and perch, well, they're not nearly as active as trout. And they can actually survive in a warm lake like Lake Powell. But trout do not. So, why can catfish, bass, and perch survive well at Lake Powell? They don't need as much dissolved O2. So they don't require as much O2 AQ. Alright, then we shifted gears again and we talked about pressure and its effect on solubility. And we said, how does an increase in pressure affect the solubility of solids and liquids? And we said that an increase in pressure has, no effect. In fact, I think I'm supposed to use the E form of effect here on the solubility of solids in liquids. So increasing pressure does nothing. However, how does an increase in pressure affect the solubility of gases in liquids? And so an increase in pressure will increase the solubility of gases in liquids. And we said once again, think about soda pop. Right? So when you open up a 2-liter bottle of soda pop or a can of pop, as soon as you do that, don't you hear the release of pressure? Soda pop is stored under high pressure so that the carbon dioxide dissolves in the liquid. As soon as you open up that top, and if it's a 2-liter bottle and you looked at it, you can actually see bubbles of carbon dioxide coming out of solution because the pressure has dropped. So increasing pressure for gases will increase the solubility of those gases. Alright, now we're going to stop there for right now. Next time, the next video, we're going to do a little bit of math. So we're going to talk about solution concentration, and we're going to do that quantitatively. So stay tuned for that.